Okay, before we actually apply the computation we have discussed to calculate the derivative, the gradient of the input using the gradient of output in the back propagation step of the convolutional neural network, we need to address a technical issue. Look, in the of the convolutional neural network computation, given the input of the operation, and we take the output, we take the convolutions by you know scanning the kernel from the up left corner, go all the way here, back here, and go all this way until we reach here. So corresponding to the output, this will be the size of our output. So basically, the output is smaller than the input in practical processing the data. Of course, you can artificially handle the boundary conditions, but here is the most straightforward handling of that. We stop computing when we haven't valid information to compute with. But here, to apply what we have discussed in the backward computation, we faced a problem. For some of the input, such as the one here, it contributes only to part of the output that is less than the full range of the kernel as we discussed. For example, someone here contributes to the output when the kernel is here, maybe here, and when we move the kernel, it contributes to here, and we move the kernel again, it contributes to here, so on and so forth. However, this guy can only contribute to here. So we don't have, when we try to do the convolution of the output with the flipped kernel, we don't have enough element to contribute to. But now we have the principal way of how to handling the missing information of the reverse side of the convolution. That is because we know when it has no contribution, we can fill zeros in this side of a convolution. We just need to pad zeros around the output, and we compute the convolution of the flipped kernel here to get the contribution of this element, and do this, so on and so forth. And now let us form a flipped, a padded input for the backward propagation computation of the convolution. Okay, so here, let's see. Now we want to compute dA given dB. Okay, we want to have a dB padded. We allocate zeros of so this is 5 by 6, and the kernel is 3 by 3, so we will need 7 equals 5 plus 3 minus 1, and 8 of this, and we will copy the element of the dB to dB padded. Oh, 3D, okay. So the start from 0, 1, and 2 2 2 plus 5 equals 7. 0, 1, and 2. 2, 2. Really? 5. Oh, excuse me. We need 2 more. That is because. Okay, sorry. It's my fault. I do not need 2 more. 7 and 9. Okay. That is because dB will have the size of 3 by 4. So we only need to fill in 3 rows and 4 columns. 2 to 6. Another typo. Let's see if we have the desired tree. Yes. Now we are able to apply 3 by 3 kernels on this array, where it computes with all valid elements in this array. Okay, in the next video, we finally will start computing the derivative, the gradient with respect to the input.